continue our discussion on the frequency response of an amplifier, and we were talking about the lower cutoff frequency. I am sure you remember that coupling capacitor is responsible for the lower cutoff frequency, and the expression which we arrived, which we can put in a generalized form, the condition for cutoff was when the capacitive reactance is equal to other serial resistances in the circuit. So, in general we can write that capacitive reactance X, this has to be equal to R effective resistance, effective serial resistance, and F C, the cutoff frequency, the lower cutoff, this comes out to be 1 by 2 pi R effective into C. So, this is the expression by which we can calculate the lower cutoff frequency, and that depends on two parameters, the effective serial resistance in the circuit and the value of capacitance which we are using. This is true for any RC network, and the amplifier network or any circuit can be converted into the prototype, and the prototype is this, that this is the effective resistance and this is the capacitance, and this can be converted into that prototype, and here the R effective will be the effective resistance of these two resistors and this capacitance. To give you an idea of the quantities involved, let us take an example. As an example, let in a amplifier the source resistance is 500 ohms, and the effective resistance between base and ground is R in, this is equal to 3.5 kilo ohms. Then R effective becomes equal to R s plus R in, and this is equal to 500 ohms, which we can put as 500 kilo ohms plus 3.5 kilo ohms. So, this is equal to 4 kilo ohms. This is R effective, and let us say that if lower cutoff is to be kept at 40 hertz, then let us find out what is the value of capacitance which we are supposed to use. So, we can use that relation that F C 1, the lower cutoff, this is equal to 1 by 2 pi R effective into C. This we can apply and we can calculate. C comes out to be 1 by 2 pi is 3.14 into effective resistance, which is 4 into 10 to power 3, because we have to substitute in proper units, and the proper unit for resistance is ohm, and into that frequency in hertz. So, it is 40 hertz. So, this is the value of capacitance. When we calculate, it comes out to be, C comes out to be 1 microfarad. 1 microfarad is to be used with a amplifier in which we have taken the source resistance as equal to 500 ohms, and the impedance looking between base and ground we have taken as 3.5. Then the capacitor which we are, the coupling capacitor which we are supposed to use that comes out to be of 1 microfarad. Now, if the lower cutoff frequency what we have taken as 40 hertz, if it changes to further lower, for example, if it is to be kept to 20 hertz, then this will be doubled. The capacitance by the same expression it will come out to be 2 microfarad, and if the frequency increases, if it goes for example to 80 hertz, then half microfarad, 0.5 microfarad capacitance will be enough to couple effectively and to give that value. Now, let us see, this was the general discussion applicable to any kind of circuit, any kind of amplifier, whether it is CB or CE and CC, whatever it is. Now, as I said, common emitter amplifier is most widely used. So, let us take the case of the common emitter amplifier. The circuit is this. These are the coupling capacitors C1 and C2, and this is the bypass capacitor CE, and here we connect the input signal Vs, and this is Rs. Now, since there are 3 capacitors, I said that the expression which we have developed, that is true for coupling capacitors as well as bypass capacitors. Then there are 3 capacitors, and hence there will be 3 cutoff frequencies, and expressions, basic expression we have developed earlier. So, this, because of the first coupling capacitor, the lower cutoff F1 due to capacitance C1, this will be equal to 1 by 2 pi Rs plus Rin into C. Rin is, this is R1, this is R2. So, whatever is the impedance here, this is Rin, effective value we are supposed to know. This is the first cutoff. Then similar expressions will be F1 because of the capacitance C2, capacitor C2 at the output circuit, here 1 2 pi R out plus RL into C. Here what is the impedance? This is as seen here, this is equal to Z O, Z out, R out, R out, and this is this capacitance, capacitor C2 couples the signal to the load. So, that capacitance C2 will come. This is the second cutoff. Third is because of this bypass capacitor CE, and that expression we can write F1 because of C e, this is equal to 1 by 2 pi R e effective. That means, with the emitter lead, what is the effective capacitance, and into C. This is the third cutoff. Here R e effective, this is equal to normally the resistance which we are using with the emitter lead in parallel with R e prime, that dynamic resistance of the emitter. So, this effective will be equal to this. Now, the three values we will get, but in the response, the response is this is the response here, this is the gain and this is the frequency and this is f1. Now, here we are getting 3 cutoffs for the lower cutoff. Now, whichever, this is important, out of these 3, the magnitude of highest one, whether f1 c1 or f1 c2 or f1 ce, whichever has the highest, that will be responsible to give, that will be the lower cutoff. And why highest one? For example, if these are 3 cutoffs, one is for example here, the other goes for example here, and the third one goes here, then obviously this cutoff will come because of this, because when we decrease the frequency of signal, then the cutoff will start right from here, they will come later on. So, out of the 3, whichever has higher magnitude of cutoff, that will give, that gives f1 in this, the lower cutoff. So, remember that lower cutoff comes from coupling and bypass capacitors. Normally it will come out of the 3, the C1 will be responsible, that first coupling capacitor will be responsible for the cutoff. Now, from where once the frequency we increase, then the voltage AC signal drop across these coupling and bypass capacitors, this keep the reactance will go on decreasing, and finally the drops will be so small that we can neglect. And when we come to the mid frequencies, we can assume these bypass capacitors, coupling capacitors as short, they are as best acting as a short. Now, what gives rise to this upper cutoff? Beyond a certain frequency, for example from f2, this gain falls further, keep on falling as we increase the frequency. Here for the upper cutoff, this is important, for the upper cutoff there is the role of coupling capacitors and bypass capacitors is completely ruled out. They are taking as short and keep on increasing the frequency, then they are better shorts. Then what gives rise to this fall in gain? These are the junction capacitances. Every device, every active device, whether it is a bipolar transistor or a field effect transistor or a MOSFET, they all have junction capacitances associated with it, and they are responsible for the upper cutoff. Now, in this upper frequency analysis, we will be needing one more theorem, and that theorem is Miller's theorem. Miller's theorem. In electronics we are using few theorems, the Kirchhoff's voltage law and Norton's theorem, these we have been now very familiar. This is Miller's theorem, which transforms the circuit for our advantage, and we can get the values which we can use for analysis. For example, where the Miller's theorem is applicable, if we have a situation like this, this is an amplifier and its gain AV, which is the ratio of V out by V in. Here this is the input port, this is the output port. We give a signal V in and we measure V out, and the ratio of the two is gain. Now here Z, if this is the situation, what is the situation? That the one end of the impedance is connected at the input of the amplifier and the other end of the impedance is connected to the output. How to analyze this circuit? How, when we are taking for example the impedance at the input into consideration, so what will be the effect of this Z, what will be the magnitude of Z at the input, how we can know? Similarly, what will be the impact, what will be the magnitude of this impedance at the output terminal, so that we can further take the analysis. This Miller's theorem gives this transformation, and this circuit from Miller's theorem can be converted into the equivalent circuit this is V in, this is V out, and this is impedance what we call Zi Miller, and this is the impedance that is Z out Miller. This is the amplifier with gain AV. This can be transformed into this, where this is the equivalent impedance which is given by Miller, and I write the expression for it. Similarly, at the output, what will be the effect of this Z, that is ZO Miller, and the expressions for the two are Zi Miller is equal to Z is that impedance and 1 minus AV. This is Miller's theorem. Miller's theorems give that if you face a situation such that the impedance has one end connected at the input and the other end connected to the output, then at the input this will be the value of the impedance. Here AV is voltage gain of the amplifier, and this is very important, this has to be taken with proper sign. AV to be used with proper sign. You remember that C amplifier, which is most widely used, there is a phase inversion at the output. That means input and output have a phase change of pi. So, for C amplifier we will take examples and we will see that AV is to be used as minus AV, where this minus sign indicates phase reversal. When we are going to use it for common collector, the emitter follower, then there is no phase inversion and AV has to be used as AV. So, this is at the input side, this is the impedance, and at the output Z out Miller, this is equal to Z AV by AV minus 1. This is the expression 4 and 5. This comes from the Miller, this is Miller effect, Miller theorem. Miller theorem gives the transformation of the impedance at the input and output if the configuration is such, and we will take examples where this will be the real situation, where one end of the impedance is connected at the input, other end is connected to the output, then it will have a equivalent of this impedance at the input and this at the output. Now, two practical cases, Z we have taken in general, but now I will take the two special cases of interest, two practical cases of interest. Case 1, where Z is a pure resistance, that means a resistance is connected, appears in the circuit such that its resistance, the one end is connected to input, other end is output. So, case 1, Z is pure resistance, let us call this, say this resistance is R. Then instead of Z in the above expression 4 and 5, we can write Z in Miller, that means at the input end what will be the influence of this resistance R, this is Miller R over 1 minus A V, and at the output R out Miller, this is equal to R A V minus 1. Let us see for a C amplifier, for a common emitter amplifier, for a common emitter amplifier, since AV is equal to minus AB because of the phase reversal, then we substitute here with the negative sign, so that R in Miller becomes equal to R 1 plus A V. A V is very large, say 100. So, the influence of this resistance when Z is equal to R, the resistance, this is the shunting effect much reduced here in this configuration, and this is much reduced. If it is, say, R is 100 K, let R be 100 kilo ohms, and if gain also we take as 100, then R I effective due to Miller will be just from 100 K, it will be reduced to 1 K kilo ohms in shunting in parallel between this terminal and ground, because normally these terminals, one terminal at the input and the other at the output, they are grounded. So, this is this is the impedance at the input due to Miller's theorem, and this may be a deciding factor. This is a big influence at the input impedance. And at what happens at the output for the C amplifier? R out at the Miller, this is R minus A V by minus A V minus 1. So, this is obviously very close to R. So, whatever is the value of resistance that appears in shunt form to the circuit. So, this is when R was purely a resistance. Now, let us take the, because we will be concerned with the capacitances when we say junction capacitance, and some junction capacitances will appear in Miller's configuration, and their influence we will see that the magnitudes are drastically changed due to Miller effect. See here case 2, this is when Z is a capacitor. Let that capacitance be, say, a capacitance C. If in this configuration a capacitor is connected, then what will be the effective value of capacitance at the input and at output, that we will see. Let X C is the reactance of the capacitor at frequency f, signal frequency f. Then according to this expression, Z, the impedance at the input due to Miller, is X C by 1 minus A V, which is 1 by 2 pi F C into 1 minus A V, and this can be put in the form, this is equal to 1 by 2 pi F into Miller C Miller, where C Miller we have put for C into 1 minus A V. This is at the input, remember this expression, C into 1 minus A V, and at the output Z out is equal to X C into A V minus 1, and this we can write as 1 by 2 pi F C A V minus 1, and which can be put in the form again as 1 by 2 pi F C out Miller, C out Miller, where C out Miller is equal, we have written for C A V minus 1 by A V. So, these are the two expressions, this is at the output and that is at the input, and let us see what they will be for a C amplifier. for a C amplifier, since AV is equal to minus AV, then C in Miller, this is equal to C into 1 plus AV. The capacitance at the input which will come in the shunt at the input is multiplied almost by the voltage gain. As I said, for a same CE amplifier, voltage gain is quite high, and so capacitance which will come in shunt form will be increased from C to C into the product C into AV, the voltage gain, very high value, and this is Miller capacitance. Miller capacitance, very high value because of this high value of AV, and at the output C out Miller is equal to C minus AV minus 1 by minus AV. So, this is equal to C at the output. So, the what will be the value here? This is the amplifier. Let us say gain, voltage gain is 100, and if this capacitance was 1 microfarad, this value is 1 microfarad, then the value at the input and output we can calculate from here. Gain we have taken as 100. So, C in Miller in this particular example will be equal to 100 microfarad from 1 microfarad. So, here this is the amplifier AV 100, and this capacitance C in Miller, this will be 100 microfarad, and what will be at the output this capacitance C out, this is C in, this because of the Miller effect will come out to be just 1 microfarad, because the C out Miller comes out to be close to C, and C we have taken as 1 microfarad. So, at the output it will be 1 microfarad. This is a big effect at the input. At the output it remains the same as it appears in the circuit. So, this is about the Miller effect, Miller theorem, and we will use these results. So, remember the fundamental expressions of that how the impedance gets modified in the two cases that we have to take, and the fundamental relations are these, that at Z I Miller, Z divided by 1 minus A V, and Z out is Z into A B y A B minus 1, where A B the voltage gain is to be used with proper sign, and A B is negative for CE, but it is positive for common base and common ammeter circuit. Now, we can go ahead with high frequency response of the amplifier. High frequency response of an amplifier. By high frequency response, that what will happen when the signal frequencies are above the lower cutoff and mid-band frequencies, where coupling capacitors and bypass capacitors have no role to play. I said that junction capacitances are responsible for the upper cutoff, and these junction capacitances, they are modified when we actually take into account the Miller's theorem, and some are amplified drastically and they have a effect, they affect our performance quite a bit. So, let us first draw the circuit, and I can just, to save time, I can go straight for the AC equivalent circuit of the C amplifier, which I have drawn earlier, and we can take these capacitances, coupling capacitances and bypass capacitances, we will take as a short. So, when we short it, for example, this resistance disappears and so on. So, the AC equivalent of the amplifier circuit is this. I am sure you remember that when we draw the AC equivalent circuit, capacitors we have taken as short, that was one condition, and the other is that DC voltage sources have to be brought to 0, they are grounded. So, VCC we ground, and that capacitor, once it is taken shorted, this is RC, this is RL, and these are the two resistances, this is the source resistance and this is the AC signal Vs. This is the equivalent circuit, AC equivalent circuit of the amplifier. Now, what are the capacitances associated with it? One is between base and collector, there is a junction. Now, there are two junctions, the emitter junction and collector junction, and hence we will have three capacitances. This between base and collector, this we say CBC. CBC is the junction capacitance between collector and base, and this capacitance we call CBE, that is capacitance between base and emitter, CBE. And third one is this one, from here to here, and this we say as CCE. That means capacitance between collector and emitter, this is CCE. So, what is the effect at the input of these capacitances, and that we have to see. Now, here comes the Miller theorem. First thing, that we are not concerned at the moment for the output, therefore, we can drop this capacitance between collector and emitter. When we are talking of input, then these two capacitances will be coming in the calculation. Now, the first capacitor between base and collector, this will come in the Miller configuration, because its one end is connected at the input, the base, and the other end is connected to collector, the output. This is in Miller's configuration, and hence what will be the influence of this capacitance CBC at the input, this we can know only from the Miller's theorem, and we have seen the capacitance that is effectively multiplied by AB, and so since CBC is in Miller's configuration what will be the influence of this at the input? It will come from Miller's theorem, and this is CBC Miller, this is equal to CBC actual capacitance multiplied by 1 plus AB, where AB I have taken for C amplifier, this is the C amplifier for CE amplifier. AB is very large. If it is 80, this may be small, this is normally the small capacitance, but when multiplied by AB becomes large. So, and this is going to affect the high frequency performance of the circuit. You remember that this comes in shunt form, this is the amplifier, this is the amplifier, then this is this capacitance C BC Miller, very high value because of the product of CBC with AB, and this is the two are in series. So, this will be added up, they will come in parallel, I am sorry, because this is between base and ground, and this is also between base and ground, this, and then the other capacitance here which is CBE between base and emitter. Therefore, at the input what will be the capacitance? Let us call total capacitance at input of the amplifier, this is C I for input, this will be C B E plus C B C into 1 plus A B, this is the total capacitance. Junction, these junctions originally they are from the junction capacitances, and resistance as seen from base towards the source and resistance as seen from base towards the source this will be R I at the input, this is R S in parallel with R 1 R 2 combination, the biasing resistances in parallel with the input impedance. When we draw the equivalent, then these two resistances will come in parallel, and to this will come in parallel this impedance, and this is we have called it Z I base. When we calculated using R parameters, then we called this as Z I base, and if you remember that this was, you should remember this is equal to, if beta is the current gain, then R E effective, here effective is only whatever is the dynamic resistance of the emitter junction. So, this has to be in parallel with this. So, this is beta R E prime, this is the total input resistance as seen between the base terminal and the ground will be this, where these three will be in parallel, and then the upper cutoff can be written from the general principle. Upper cutoff is actually 1 by 2 pi R C. What are the values of R, what are the values of C, they will decide the cutoff, and these are the values. The input capacitance is this much, and input resistance is this much, and so upper cutoff we may call it the first. This comes out to be 1 by 2 pi r I and C I. This will give the cutoff frequency. Here we have, so this is one value, let us call equation 6, and then so far we have been neglecting one resistance, that is base spread resistance. Now, so this is from the input, and because of the output, if we look at the output, then another cutoff will appear and we call it 2, and this is equal to 1 by 2 pi r 0 C 0, where C 0 is what is the capacitance at the output. Now, this will come C C E C C E between capacitor and emitter and any other capacitance. In any other, there are two things. We have been neglecting the lead capacitances and the stray capacitances. Stray capacitances are when there are several conductors in close proximity and the currents are flowing through them and they are separated by insulator. They also have a capacitance associated with that, and that we call stray capacitances. Stray, at low frequencies their magnitudes are negligibly small and we never talk about these capacitances. So, self capacitances of leads, stray capacitances, they acquire significant magnitude and they start influencing the high frequency performance. So, this is the capacitance, and the R will come out to be R 0 is the effective value of the resistance with the capacitance lead. So, this is the two resistances are in parallel, this is ground, this is ground. So, what is the impedance, equivalent impedance between this collector and ground? That is equal to R C in parallel with R L. So, this is that and in addition to this capacitance there will be that because of Miller effect. You remember that C B C at the output from Miller's theorem comes out to be of the same magnitude. So, the total capacitance will be, this is C B C plus this let us call it due to Miller, this C O which contains C C E and other capacitances, and this will give another cutoff frequency, and this will be the second cutoff frequency, upper cutoff. We are talking of upper cutoff. First we have seen that the upper cutoff comes because of this capacitance at the input which gets magnified because of Miller's effect. The other is at the output there are other junction capacitances which are equal to this and resistance is equal to this. This will give another cutoff, and that cutoff is this. There is third cutoff. At high frequencies beta falls, beta starts falling at high frequencies. This is because of the transport processes involved that what gives rise beta as a high value. When we increase the frequency of operation, then those processes are not as complete as at the low frequencies, and hence the current gain falls. Current gain falls, and if at midband here, at midband, if the gain is beta, then you remember that it has to be at cutoff frequency, it has to be 70.7 fraction of this, that means 0.707 beta at upper cutoff. Now, manufacturers give another value which we have talked earlier, Ft. Ft is the frequency at which gain falls to unity. Frequency at which gain falls to unity, and it can be shown that f beta is related with f t by beta at midband. So, this will give the third cutoff. There are at input there were 3 cutoff frequencies arising from the 3 capacitors, 2 coupling capacitors C1 and C2 and 1 bypass capacitor, that was CE, and whichever was higher frequency, that will be responsible for giving F1. So, that F1 will be equal to that frequency. In this case, there are 3 frequencies arising from 3 different factors. This third one is from the fall in gain beta with the frequency, and that we have seen this is equal to this, and the other 2 are because of the junction capacitances at as seen at the output and input of the junction and of the circuit. So, the 3 will be, and whichever has lower, this is important, lower cutoff has to be the highest one gives F1, here the lowest of the 3 will give upper cutoff. This one. This analysis is applicable for a bipolar transistor or for a field effect transistor. In field effect transistor, this R in is normally given as GM, the transconductance. So, R in this will be equal to GM, because conductance is inverse of resistance. We will continue.